Lecture 7, Measures of Spread. So let me remind you that last time we talked about measures of central tendency. We talked about parameters and statistics for a numerical variable, which told you where the middle or typical value was. That's the most important thing to say about a numerical variable. But the second most important thing to say is how spread out the values are around that middle. So before we talked about the mean and the median. Today I'm going to focus on the mean and ask how spread out the data is around the mean. The thing that measures that is the standard deviation. You should take that as the typical distance of a data value from the mean. I'm going to take a little while before I get to the definition, because the definition is a kind of complicated formula and is not the most important thing here. The first thing I'll tell you about is its name. Of course, it's got two names depending on whether you're in the population context or the sample context. The population standard deviation is kind of a mouthful to say or to write. We'll usually abbreviate it SD or STDEV or various things like that. The population standard deviation is referred to by the Greek letter sigma. It's pronounced sigma. It's written like, I think of it as an O with a baseball cap, an O with a tail at the top. It's the ancestor of our S for standard deviation, but doesn't look very much like it. You might be able to argue it looks like a cursive S, I don't know. The sample standard deviation is denoted by the Roman letter S. Most important thing about the standard deviation is the empirical rule. The empirical rule describes what the standard deviation tells you in a useful heuristic way. Okay, it has three versions. This is a rough rule of thumb. It works very well if your data is symmetric and unimodal. So remember, that means bell-shaped. And it works reasonably well if your data is not too far off from that. If it's highly skewed, this won't tell you much. Comes in three versions. First, about 2/3 of the data falls within one standard deviation of the mean. So what does that mean? It means 2/3 of your data points are a distance of sigma, the standard deviation from the mean mu, or less. Or to put it another way, they fall between mu minus sigma and mu plus sigma. In the next slide, I'm going to show you a picture which might make this a little easier to process, but let me get through the other two. So that was 2/3 of the data are within one standard deviation. Most, but not the overwhelming majority. About 95% of the data fall within two standard deviations of the mean. That is, somewhere between mu minus 2 sigma, lower bound, and mu plus 2 sigma is the upper bound. 95% is the great majority. When this fails, it's unusual, but not shocking. And then finally, almost all of the data falls within 3 standard deviations of the mean, or between mu minus 3 sigma and mu plus 3 sigma. Anything outside that range is shocking. So here's the short version. When we talk about the standard deviation, it will almost always be talking about distances from the mean. You'll have to get used to thinking of the standard deviation as being the scale on which you measure distance from the mean. Okay, here's my picture. On the right you see a perfectly symmetric unimodal distribution. Right in dead center there's a red line labeled mu. Why is that? That's because we know that the mean is represented on a histogram by the point on the x-axis where it balances, which of course is right in the middle. When I talk about within one standard deviation, I'm looking at the red line immediately to its left and to its right, which are labeled mu minus 1 sigma and mu plus 1 sigma. All the points between those two red lines are within one standard deviation of the mean. Stop, make sure that you see that what I'm saying makes sense, because it's simple but a little bit contorted and unusual. Okay, and then in this figure, which I stole off the internet, they said about 68%. That's about the same as 2/3. And 2/3 is the simpler thing to remember. 2/3 of all that data falls between those two red lines. And if you think about the total mass of yellow in that picture, about 2/3 of it falls between those two red lines. That seems about right. Next, we go up and down 2 sigma. The red line 2 below the mean and the red line 2 above the mean are labeled mu minus 2 sigma and mu plus 2 sigma. And about 95% of all the yellow in that figure falls between those two. And finally, if you go all the way down to mu minus sigma, 3 sigma, and mu plus 3 sigma, you get, in this figure, 99.7%. But more roughly, we'll say almost all. But this isn't going to really make sense until we do an example. So here's my example. We saw before that when you look at people's heights mixing men and women, you get a bimodal but reasonably symmetric distribution. And I asserted that that was because of the gender. Everybody seemed to think that. And that if we had looked at either men or women separately, we would get a symmetric unimodal distribution. That's in fact true. So to be precise, let's look at college-age women. Their heights are symmetric and unimodal. Their mean height is 65.5 inches, so that's 5 foot 5.5, and their standard deviation turns out to be around 2.5 inches. When someone tells you that, you immediately know 3 things. You know that if I go up and down from the mean 1 standard deviation, so if I add and subtract 2.5 from 65.5, I will get 63 inches on the bottom and 68 inches on the top, which is to say 5 foot 3 and 5 foot 8. So this is telling you that you should expect 2/3 of all college-age women to have a height between 5 foot 3 and 5 foot 8. If you think about the college-age women you know, that should seem roughly correct. Most fall in that range, but not the overwhelming majority. Likewise, if we go up and down 2 standard deviations. So 2 standard deviations is 5 inches. If we add and subtract 5 inches from 65.5, we get 60.5 and 70.5, which is 5 feet and a half inch to 5 foot 10.5 inches. So that's going between the 2nd and 6th red line in the figure. And this would tell you that 95% of college-age women have a height between 5 foot and a half inch and 5 foot 10.5 inches. Again, think about the college-age women you know and see if that's reasonably plausible. Out of every 20 women, on average, 1 should fall outside that range. Either be taller than that or shorter than that. You can think of people who fall outside that range as being unusual. A woman who's over 5 foot 10.5, unusually tall. A woman who's under 5 foot and a half inch, unusually short, but not shocking. Okay, you might want to pause here and see if you can fill in the 3rd version. It's just a repeat of what I've done. Make sure you're getting it. Now we'll add 3 standard deviations. 3 times 2.5 is 7.5 inches. And we will see that we add and subtract 7.5 to the mean of 65.5, and we get from 4 foot 10 to 6 foot 1. So that's 58 inches and 73 inches. And the final claim is that almost all women are between 58 inches and 73 inches, between 4 foot 10 and 6 foot 1. A woman outside that range is extremely unusual. Of all the college-age women you know, maybe one of them falls outside that range. 3 standard deviations is extremely unusual. Notice that standard deviation and the mean have the same units as the variable. Height is measured in inches, so mean and standard deviation are in inches. Okay, that's the empirical rule. Finally, I get to tell you the formula for the standard deviation. Because it's a kind of complicated formula, I'm going to tell it to you in steps. The first thing you do, remember, the standard deviation is telling you the typical distance of a data point from the mean. So the first thing we do is find the distance of each data point from the mean, which is to say we subtract them. So we take each data value minus the mean. Remember, we call the data values x1, x2, up to xn. N is the number of data points. So we'll take x1 minus mu, x2 minus mu, and so on. And then the second step is we square each of those distances. The idea is that some of these are negative and some are positive. So if we want to think of them as distances, that doesn't really make sense. So we square them to get rid of the sign. So now we have x1 minus mu squared, x2 minus mu squared, x3 minus mu squared, up to xn minus mu squared. And the third step is we average them. We take those numbers, those formulas, we add them all up, and we divide by how many there are, n, the number of data points. And the last thing we do is take the square root of that. So the formula for the standard deviation is the square root of, on the top you have the sum of the squares of the differences, and on the bottom you have n. I'm just going to point out one thing that we will not ever look at again in this class, which is, if you ignore the divided by n, this is a lot like the formula for distance in 2 and 3 dimensions that you probably learned in pre-calculus or something like that. You remember there, you take the difference of each coordinate, you square them, you add them, and you take the square root. This is a very geometric definition. It works very much like distance. And a lot of the mathematical power of the standard deviation and a lot of the techniques we use from here on in rely on the analogy with geometry. Okay, let me show you how to calculate the standard deviation in a very simple case. Here's my simple case. I have 2 data points, the numbers 0 and 4. The first step is to find the mean, and of course, the mean of 0 and 4, 0 plus 4 over 2, is 2. Okay? So the first step, and it's nice to make a little table like this, is to take each data point minus the mean. So 0 minus 2 is negative 2, 4 minus 2 is 2. The second step is to square each of those numbers. Negative 2 squared is 4, 2 squared is 4. Third step is to average them. The average of 4 and 4, of course, is 4. And finally, we take the square root, and we get 2. So that's telling you the standard deviation of that data set, the numbers 0 and 4, is 2, the population standard deviation. That's supposed to be the typical distance of a data point from the mean. So, of course, the typical distance of 0 and 4 from 2 is 2. They're both distance 2, so that's reasonable. It is not a unimodal distribution since it has 2 data points. You could call it bimodal. So we shouldn't take the empirical rule too seriously, but the empirical rule would tell us 2/3 of the data falls within 1 standard deviation of the mean, that is between 0 and 4, while all of the data falls right on the boundary. So you decide whether that is a reasonable interpretation or not. Okay, now I have a little bit of a confession to make. We've been talking about the population standard deviation. Now I want to talk about the sample standard deviation. Just like in the mean, the distinction is so important, we use a different symbol for it. But life is even a little bit more complicated here because we use a slightly different formula as well. The mean, whether you were talking about x bar or mu, use the same formula, right? You add up all the numbers, you divide by n, the number of data points. Here, it's going to be almost the same formula. This is going to be a slight annoyance that you'll have to be aware of, but not have to worry about otherwise. But the underlying reason is, and later in the semester we will talk about this a bit, that you want the formula that you compute in the sample that does the best job of approximating the population standard deviation. And it turns out, for deep mathematical reasons, that the thing you can compute from the sample that best approximates the population standard deviation is the sample standard deviation, whose formula is as follows. It's exactly the same as the population standard deviation, except for two differences. One is, instead of mu, we use x bar, right, because we're looking at sample, so of course we use the sample mean. But the important difference is, instead of dividing by n, the number of data points, we divide by n minus 1. So if you have a data set of 20, instead of dividing by 20, you divide by 19. If you like, you can think of it as computing x bar used up somehow one of the data points. That probably doesn't help any, but that kind of fits how statisticians think of it. Anyway, the effect of this, because you're dividing by n minus 1 instead of n, is to make the sample standard deviation slightly different, slightly bigger than the population standard deviation. So there are two important things to remember about population and sample standard deviation. The first is their formulas are different. The second is you shouldn't stress about that. By and large, when someone says find the standard deviation, they mean find the sample standard deviation. Why? Because if you're finding it, then you must be using actual data, which means you're probably using a sample. Okay, and I'm not sure why I'm mentioning it here, but the standard deviation is sensitive to outliers. It's not a good idea to use the standard deviation when you have extreme data points because they have a big effect on the standard deviation, even more so than the mean. So let's calculate the sample standard deviation in the same example. Two data points, 0 and 4, but now we're thinking of them as a sample. You might want to try this first. It's very similar to the calculation we did before, except for dividing by n minus 1. Try it, and then see if it works out the same as mine. Here we go. We start with 0 and 4. As before, we subtract the mean. 0 minus 2 is negative 2. 4 minus 2 is 2. As before, we square those two numbers. Negative 2 squared is 4. 2 squared is 4. But now, instead of averaging them, we add them to get 8 and divide not by n, which is 2. 2 is the number of data points, but by n minus 1. 4 plus 4 divided by 1 is 8. And then finally we take the square root, and we get the square root of 8, or 2 root 2, which is about 2.83. As I said, the sample standard deviation is bigger than the population standard deviation. In this case, where there's only 2 data points, it's noticeably bigger. Usually it's microscopically bigger. Usually it's a trivial difference. My sister is an engineer, and she remembers vividly the first conference she went to when she was not too much older than all of you. Somebody started talking about the standard deviation, and some theoretical type asked whether it was population or sample, and they started arguing back and forth. And she was like, these people are crazy. Nothing about our problem is at all accurate, and they're worrying about things that are off by a tiny decimal place. Alright, here's what you should be able to do. Having watched the lecture, you should be able to apply the empirical rule if somebody tells you the mean and standard deviation, and use that to get a rough sense of what the standard deviation tells you based on the empirical rule and its interpretation as a typical distance from the mean. That's the most important thing. You should be able to very roughly estimate the standard deviation from a histogram. What do? You find the mean as the balance point, and you ask yourself, how wide around that would I have to go to get about 2/3 of the area? Gives you a rough sense of the standard deviation. And thirdly, you should know not to use the standard deviation to summarize a skewed distribution. As I said in the beginning, the standard deviation goes along with the mean, and you should only use it in situations where the mean makes sense, which is reasonably symmetric data. and even more so because the standard deviation is so sensitive to extreme values, and because your basic understanding of the standard deviation comes from the empirical rule, which breaks down for skewed data. And finally, after we've worked with this a little bit, you should be able to understand that there's a difference between the population and the sample standard deviation. You should be able to use the standard deviation formula to understand basic properties of the standard deviation. For example, because it's a square root, it's never negative. That's an easy property, and to compute it for very small data sets, say 2 or maybe 3 data points. And finally, we will see how to calculate population and sample standard deviations in Excel.